Welcome you all. On this session, I will explain about how to solve numerical on Pelton wheel turbines. So take down first numerical on this one. There is a problem number 1. The problem is like that. So it is desired to generate 1000 kilowatt of power, and survey reveals that 450 meter of static head and minimum flow of 0.3 meter cube per second is available. Comment whether the task can be accomplished by installing a Pelton wheel that turns 1000 rpm and has an efficiency of 80%. Further design the Pelton wheel by assuming suitable data for coefficient of velocity and speed ratio. So now write the given data for this numerical. So now here there is a this numerical is related to Pelton wheel turbine. So now Pelton wheel turbine is designed to generate the 1000 kilowatt of power. That means the desired power is 1000 kilowatt. Here the head is maintained at the H is equals to 450 meter, and flow rate through the Pelton wheel turbine is, that is a Q is equals to 0.3 meter cube per second. The first part of the numerical is to check whether this given condition, whether the suitable or Pelton wheel is suitable or not. So now this Pelton wheel is operating at the speed of 1000 rpm and an efficiency of 80%. The second part of the numerical is to design the Pelton wheel by assuming a value for coefficient of velocity, that is a C of V, and speed ratio 5. Now given data is like that. The P is equals to 1000 kilowatt, net head is 450 meter, discharge is 0.3 meter cube per second, speed N is equals to 1000 rpm, then overall efficiency of the turbine is 0.8, and here coefficient of velocity is assumed as 0.98 and speed ratio as 0.46. Now we know that the overall efficiency is a ratio of power developed to the energy available at the inlet of the rotor or turbine. So here the density, the rho is equals to density of the fluid, then G is acceleration due to gravity, Q is discharge, H is equals to head. So here overall efficiency is given as 80%, that means that value is 0.8. Then density, the water is flowing through the Pelton wheel turbine, then density of the water is 1000 kg per meter cube, G value is 9.81, the discharge is given as 0.3 meter cube per second, and head is maintained 450. By using this formula, find out what is the power developed by the turbine. After substitution of these values, then power value is obtained as 1060 kilowatt. So now here the Pelton wheel is designed to produce 1000 kilowatt of power, but in a theoretically for this one Pelton wheel will produce 1060 kilowatt of power. That means now desired power is lesser than the theoretical power generation. So for that reason, for this given condition, the Pelton wheel is suitable. Now write one comment. Since the power developed by the turbine is more than the desired power, then task can be accomplished. The second part of the numerical is to design the Pelton wheel turbine. So first of all, by using the speed ratio formula, the speed ratio is equals to U by V1. So here V1 is equals to square root of 2gh. So here speed ratio value is taken as 0.46 and head is 450 meter. So then substitute the values in this expression, then find the value of u is equals to 43.2 meter per second. Then find what is the diameter of the wheel. The diameter of the wheel is calculated by using the formula by the blade velocity is equals to pi dn by 60. The blade velocity value is obtained as 43.2. Then this Pelton wheel is operating at 1000 rpm. After that, after simplification and substitution and simplification, we will get the d value is 0.826 meter. So now in order to find out the diameter of the jet, the one assumption is made here. This is the ratio of diameter of wheel to the diameter of jet is equals to 10, and the V1 is equals to C of V square root of 2gh. So these are the two assumptions are made. So now jet diameter. So we know the value of diameter of the wheel as 0.826 meter. By using these relations, the diameter of the jet is equals to d. The small letter d is equals to capital letter D. That's the diameter of a wheel by 10. With respect to that, the diameter of the jet is equals to 0.0826 meter. Now what about the velocity of jet? The velocity of the jet is calculated by using the formula V1 is equals to C of V square root of 2gh. So here C of V, that value is assumed as 0.98. After that, we are getting the velocity of jet is equals to 92.08 meter per second. Now third one, number of jets. So number of jets is calculated by using the discharge formula. The discharge is equals to n into A of F, that is area of flow, into velocity of flow. Here the small letter n represents number of jets used. So now we know the value of discharge, and area of the flow is calculated by using the formula pi d square by 4. So here d represents the small d, that means diameter of the jet, and v of f is equals to velocity of flow. So now with respect to that, n is equals to the ratio of q by a of area of the flow into velocity of flow. Here the area of the flow is equals to calculated by using the formula pi d square by 4. The diameter of the jet value is 0.0826 and velocity of the flow is equals to 92.08. So now we are getting the number of jets is equals to 0.608. So the approximately is equals to 1. That means in this Pelton wheel turbine, the only one jet is used. Next, number of buckets required. So in a Pelton wheel, the buckets are connected to the wheel. So now how many buckets are required for these given conditions? So that is calculated by using the formula. The number of buckets Z is equals to 15 plus D by 2 into D. So here capital D is equals to diameter of wheel. The small letter d is equals to diameter of jet. Substitute the values here and Z is equals to 20. That means in this Pelton wheel turbine, there are 20 buckets are connected to the wheel. Next, find the other dimensions of the buckets, that is the bucket dimensions. So width of the bucket is calculated. So it is 3.5 times of diameter of the jet, that is 3.5 into 0.0826, that is equals to 0.289 meter. Depth of the bucket is equals to T, that is denoted by letter T, so that is equals to diameter of the jet, that is equals to 0.0826 meter. Now radial length L is equals to 2.5 into D, that means 2.5 times of the diameter of the jet, so that is equals to 0.02065 meter. So this is the solution for the given numerical. In first part we suggested whether this Pelton wheel is suitable or not for these given conditions. So later in second part we design the Pelton wheel. That means we calculated what is the diameter of jet, so what is the diameter of the buckets, so how many jets are required, so how many buckets are connected to the wheel, and what is the bucket dimensions. Next, second numerical on this Pelton wheel turbine. The penstock supplies water from a reservoir to the Pelton wheel with a gross head of 500 meter. One third of the gross head is lost in friction in the penstock. The rate of flow of water through the nozzle fitted at the end of penstock is 2 meter cube per second. The angle of deflection of the jet is 165 degree. Determine the power given by the water to the runner and also hydraulic efficiency of the Pelton wheel. So take speed ratio is 0.45 and C of V 1. After that, now write the given data here. So now water is supplied from the reservoir to the Pelton wheel turbine through the penstock. So initially in a reservoir the head is maintained at 500 meters. So while water is flowing through the penstock to the Pelton wheel turbine, so in that time the one third of the gross head is lost due to the friction. For that reason the net head is reduced from 500 to the reduction in due to the friction. The rate of flow of water through the nozzle fitted at the end of the penstock is 2 meter cube per second. That is, discharge occurs through the nozzle is 2 meter cube per second. The angle of deflection of the jet is 165 degree. So now determine what is the power given by the water to the runner and also calculate what is hydraulic efficiency of the Pelton wheel. And here speed ratio 5 is value is taken as a 4.545 and C of V is equals to 1. So now write the given data. The H of G, that is gross head, is 500 meter. The H of F, that is a head loss due to the friction, is equals to 1/3 of the Hg. The discharge is equals to 2 meter cube per second. Speed ratio is 0.45 and C of V is equals to 1. So now net head is calculated here as the gross head Hg minus head loss due to friction. So gross head is 500 meter. So here head loss due to the friction is 166.7. So that means it is 1/3 of the gross head. So for that reason the net head is available for the turbine is 333.3 meter. And here angle of deflection of the jet is given as 165 degree. Hence the beta 2 angle, the blade angle at discharge is taken as 180 degree minus 165 degree. So that is equals to 15 degree. That means beta 2 angle is 15 degree. Now velocity of jet. The velocity of jet is calculated by using the formula V of 1 is equals to C of V square root of 2gh. V1 is equals to, here C of V is taken as a 1 and head is equals to 333.3. So now velocity of jet is 80.86 meter per second. So this is a velocity triangle for Pelton wheel turbine. So So here the angle of deflection is given as a 165 degree, that is a theta. For that reason the beta 2 angle is a 15 degree. So here V1 is equals to VU1 and x2 is equals to summation of u and VU2. It is a blade velocity as well as tangential velocity at exit. So now bucket velocity is calculated by using the relation, that is the speed ratio. The bucket velocity is equals to speed ratio into square root of 2gh. So after substitution of that one, the speed ratio is given as 0.45 and net head available for the turbine is 333.3. With that, the bucket velocity is 36.387 meter per second. So now VR1 is equals to, the VR1 is equals to V1 minus U. So now we know the value of V1 as well as value of U. So that means now the value of VR1 relative velocity at inlet is equals to 44.47 meter per second. Now assume the VR1 is equals to VR2. That means there is no loss of relative velocity from the inlet to the exit. That is VR1 is equals to VR2. So now from the exit velocity triangle, so now I want to calculate the value of x2, the distance of x2. So x2 is calculated by using the trigonometric relations cos beta 2. So cos beta 2 is equals to x2 by VR2. Cos beta 2 is equals to x2 by VR2. That means x2 is equals to VR2 cos beta 2. x2 is equals to VR2 cos beta 2. So now we know the value of VR2 is equals to 44.47. The cos beta 2 angle is 15 degree. Hence, now x2 value is equals to 42.95 meter per second. From inlet velocity triangle, VU1 is equals to V1, so that is equals to 80.86 meter per second. From outlet velocity triangle, cos beta 2 is equals to x2 by VR2. The x2 is equals to u plus VU2. So in this expression, we know the value of beta 2, we know the value of VR2, to know the value of u. The only one unknown parameter is VU2, tangential velocity at exit. So now this tangential velocity at exit is equals to 6.57 meter per second. So now power given by the water to the runner is equals to, that is by using the power formula, power is equals to m into u, VU1 plus VU2 by 1000. So here m is equals to mass flow rate of fluid. So that means mass flow rate of water to the turbine. So that is calculated by using the relations, by using the expressions of our density. The density is a ratio of mass by volume. That means the mass flow rate is equals to density into volume flow rate of fluid, that is discharge, that is discharge in meter cube per second. So now m is equals to density into discharge, then bucket velocity VU1 plus VU2 by 1000. So here density of the fluid, that is water, is 1000 and discharge taking place to this Pelton wheel turbine is 2 meter cube per second. Then bucket velocity is 36.387. Tangential velocity at inlet is 80.86 and tangential velocity at exit is 6.57. So now power given by the water to the runner is 6362.63 kilowatt. Now calculate what is hydraulic efficiency and what is the value of hydraulic efficiency. The hydraulic efficiency is a ratio of, there is a meter h, is a ratio of 2 into u vu1 plus vu2 by v1 square. Here u is equals to bucket velocity, vu1 is equals to tangential velocity at inlet, vu2 is equals to tangential velocity at exit, then v1 is equals to velocity of jet. So after simplification of this, we will get the hydraulic efficiency is equals to 97.31%. So move on to the third numerical on this Pelton wheel turbine. So problem number 3, a Pelton, a double overhang Pelton wheel unit used to produce 30,000 kilowatt had generated under an effective head of 300 meter at the base of the nozzle. Find the size of the jet, mean diameter of the runner, speed and specific speed of each Pelton turbine. So now assume generator efficiency is 94%, Pelton wheel efficiency is 0.84% or 84%, speed ratio is equal to 0.46, jet velocity coefficient 0.98 and jet ratio is equal to 12. So now write the given data here. Here power developed by the Pelton wheel turbine is 30,000 kilowatt. The head available is 300 meter. Speed ratio 0.46. Velocity of coefficient C of V is equal to 0.98. Jet ratio D by D is equal to 12. And generator efficiency is 0.94 and overall efficiency is equal to 0.84. So find diameter of the jet, diameter of the wheel, then the speed of the Pelton wheel, then specific speed of the turbine. Now power at the shaft of the turbine is calculated by using the expressions. The total power developed is equals to power developed by the generator to the efficiency. So actually here double overhang Pelton wheel turbine means, so the arrangement is like that. So there are two turbines now. So this is a turbine number 1 and one more turbine is here. This is turbine number 2. Turbine number 2. The generator is connected here. There is only a single generator is connected to these two turbines. The output shaft of the turbines are connected to this generator. So now this generator is producing 30,000 kilowatt of power under the efficiency of 94%. That means the 6% of power is lost in generator. That means so these two turbines are producing more power than the power produced by the Pelton wheel turbine. Because here the efficiency is only what 94%. So now we want to calculate what is the power produced by these turbines or power available in the turbine. So that is calculated the ratio of power available in the generator produced by the generator and its efficiency. That means that is 31,914.47 kilowatt. That means now power produced by the generator is 30,000 kilowatt, but actually power produced by the two turbines is 31,914.47. So now you have to calculate what is the power produced by the each turbines. Power produced by the each turbines. So there are two turbines here. That means the power produced or developed from each turbine is equals to the total power generated by the number of turbines, that is equals to 15,957.47 kilowatt. So now calculate jet velocity. The jet velocity is calculated by using the relations V of 1 is equals to velocity coefficient into square root of 2gh, and that the velocity of jet is equals to 75.2 meter per second. Bucket speed is calculated by using the relations the speed ratio, that is a u is equals to speed ratio into square root of 2gh. So now bucket velocity or bucket speed is equals to 35.29 meter per second. Overall efficiency is equals to power developed to the power available at the inlet of the rotor, or power supplied by the water. So now here overall efficiency is known. The power produced by the individual turbine is 15,957.47. The density of the water is 1000. G value is 9.81. The discharge is unknown and head is given as a 300. Hence, now the discharge taking place through this turbine is 6.455 meter cube per second. Next, the size of the jet. So assume there are number of nozzles are 1. The size of the jet is calculated by using the discharge expression. The discharge is equals to number of jet into area of flow into velocity of the flow. So with respect to that, the n is equals to q by area into velocity of flow. After substitution of this, you will get the diameter of the jet is equals to 0.331 meter. Next, mean diameter of the wheel. The mean diameter of the wheel is calculated by using the jet ratio relations. The jet ratio is given, that is D, capital D to small letter d. The diameter of the wheel to the diameter of jet is equals to 12. So now we know the value of diameter of the wheel. Hence, the diameter of we know the value of diameter of jet. For that reason, the diameter of the wheel, capital letter D, is equals to 4.05 meter. Next, speed of the turbine. The speed of the turbine is calculated by using the formula. The bucket velocity or the speed of the synchronous speed is equals to pi d n by 60. So now we know the value of u, 35.29. We know the diameter of the wheel is 4.05, and the speed is equals to synchronous speed is equals to 166.417. The alternate method to find the synchronous speed is equals to the number of poles is equals to 120 f by n. Here n is equals to frequency, f is equals to frequency, n is equals to speed. And the number of poles are calculated as 36. And in the synchronous speed is once again similar one, there is 166.67 rpm. So now specific speed. The specific speed of the turbine. The specific speed of the turbine is given by the relation n of s is equals to specific speed of the turbine is equals to the speed of the turbine into square root of the power, that is the power developed by the turbine, to the h power, head power 5 by 4. So now we know the speed of the turbine, we know the power developed by the turbine, and also we know the value of head. Hence, now the specific speed of the turbine is equals to 166.67, that is the speed of the turbine, and power developed by the turbine is 15,957.47 kilowatts, and head is maintained at 300 and power of 5 by 4. So now specific speed of the Pelton wheel turbine is 16.86 rpm. So this is a solution for given numerical number 3. So this is the procedure to solve the numericals on this impulse turbine or Pelton wheel turbine. Thank you.